Okay, guys. We finished up to this point last time. We talked about the imperfections in solids, specifically in metals. Why the last part is not showing in this? Do that. You see the effect. Here we have the same thing. Oh. Okay, anyways, this is enough. So last time we talked about the imperfections in solids. We saw that we have different types of imperfections, basically the point imperfections, which had different types, the self-interstitial, and we had the vacancies also. We had the line defects like the dislocations. We had the area defects like the grain boundaries. We also talked about other kind of imperfections like the bulk or volume defects in the pores, cracks, and foreign particles. We also mentioned the interfacial defects such as the twinning, the stacking faults, which we said it's like the stacking faults in the crystal structure. It has an A, B, A, B, then you have suddenly A, for example, like that. And we talked also about the second phase boundaries as well. This use what we have learned already in the previous chapter and in this chapter to explain more about the plastic deformation and its relation to dislocation. Since we have learned what dislocations are so far in the last lecture, now let us learn how does the plastic deformation in a little bit more detail than what we have covered before. We already know that plastic deformation occurs due to slip which occurs in the material in certain specific favorable directions which are referred to as a close pack directions, and these occur basically generally in the close pack planes. Those slip or this slip which happens occurs due to the movement of a large number of dislocations. When the dislocations move, the slip occurs, the plastic deformation happens. When the dislocation is restricted to move, yani you restrict the dislocation to move, you hold the dislocation, you resist the movement of the dislocation, you will make it harder for the dislocation to move, it will be more hard for the slip to happen, plastic deformation will occur, will not occur easily. And that's why you have higher strength requirement in order for the plastic deformation to occur. So ductility will reduce and the strength of the material will increase. What did I do? So this is what we did before. Now we want to specifically talk about that part in the plastic deformation of the related to the dislocation movement now. Last time we said in the plastic deformation, the dislocations make metals weaker than what they should be, but also allow it to deform. If it is not the dislocations in the material, we would have had to spend a much larger force or stress in order to plastically deform the material. This is what we have said last time. Guys, are you with me?
Yes.
Yes.
I'm just checking because we had a very bad internet at home. I had to come to UOB. So dislocations, now I'm saying that dislocations, you can see my mouse.
Yes.
I'm moving, but I don't in the recording that it doesn't show. Let me put it like that. Dislocations allow the deformation at much lower stress than in a perfect crystal. So we want to find out why and how does this happen. So basically, we want to deal with today to deal with the mechanics and the mechanisms involved in the dislocation movement basically, and how does this ease the slip or the plastic deformation in the material. As we said, perfect crystals are never there. Dislocations and the other imperfections are always happening in the material. Let's see how is it that the dislocations cause the plastic deformation at much lower stress than in a perfect crystal. So let's look at this as an example of an edge dislocation, for example. This is an imperfection. This is the dislocation we are looking at. When we have a dislocation here now, this is like a half a plane inserted, squeezed into the material here in the crystal structure, and causing what? Causing, actually, when it is inserted, it is pushed in, it causes what? Internal stresses in the vicinity of the dislocation, as you could see here. We have mentioned that previously in the last lecture. So it's causing more stress here. So since this is like the self-interstitial defects there, it's not a vacancy, it causes compressive load here and compressive load there. So it's causing those compressive loads which we are looking at. Now, what happens when you are under a load? So this is a shear stress. We are looking at the shear stress here. Of course, to compensate that, there's a reaction which is on this side. So basically, this is the shear plane we are looking at. So load is from here and from here. So this is a plane, the plane where you have the shear stress. Now this shear stress, what does it do? Due to the fact that you have more compressive loads here, of course you have a compression load due to the shear stress which you are applying here. So there is compression on this, on the bones that you have here. There is also compression actually load on here due to the dislocation which is here, but the compression load is in this direction. Compression load due to this is in this direction. Now, for these bones here, these two loads deduct from each other. So the total load on these bones will be this minus that. On the other hand, the load on these bones will be this load plus that load. They add together. So there is more load on these bones than the other ones which you have there. So what happens here now? When there is a shear stress or load or stress being applied there, the load will increase until a certain load which is able to cut those bonds actually, and those bonds are the first bonds which are going to break. Why? Because the load here is bigger. The load here is this load plus that load. So the load here is bigger. So that what happens there? It pushes these actually. I mean, I'm mentioning these bonds just as an example. Let me erase that to show it in the correct way. So, yeah. So what happens here? So what happened? Where is it? So what happens here? Since this is pushing this in this direction, again these bonds are also under the same compression load. So it pushes these atoms, push these atoms to go in this direction. So these bonds are going to break first. You see, the other bonds are not in the same amount. They don't have the same amount of load as it has here. So the same thing for those bonds as well. So it pushes these atoms push these bonds actually to break, and these bonds break the first thing, and then these bonds, once these bonds are break, they don't have any bonding. So this will constitute the dislocation basically, and these atoms are going with these atoms there, and the shape will be like that. So as if you have this here has pushed those atoms there which are there, they push the atoms which are which are here, they broke those bonds there and pushed the dislocation to be on this side, and they linked from here. So the rest will be going out as a dislocation. So this became the dislocation now, as you could see it here. Again, this is actually one step. And the next step, the dislocation is here, and it's causing more stress in the vicinity of it. And again, since there is shear stress there, these bonds are under more stress than the other ones. So these atoms are pushing in this direction. These bonds are going to break, and once these break, the atoms need to go to it, to do bonding, because if it lacks bonding, it's not stable. So they bond with these, and therefore this now becomes the dislocation again. It's pushed in the other way. So it just needs to link with one set of bonds, as you could see here. So this is the next step, and so on and so forth. This is going to happen until it moves in that direction, the dislocation. So this is basically the direction of the movement of the dislocation in this way, which is basically shown by the in the direction of the slip plane. Obviously, this movement of the dislocation would be also a close back direction. Why? Because in the close back direction, the energy required for the slip to happen is less than the other directions. So this is how the dislocation moves. It moves like it is basically a stepwise breaking and reforming of bonds. And so it's like the movement of the worm. حركة الدودة. شلون الدودة تتحرك؟ It moves like this in a stepwise manner. It doesn't happen it happens step by step. It doesn't happen in one time actually. If the bonds in a perfect crystal, let's look at this part for it. Let's look at this part for example. This is a perfect crystal. If the breaking of the bond was supposed to happen in one time, because this is missing some bonds there as well, so let's put it correctly. So if plastic deformation was to happen in a perfect crystal, all those bonds needed to be broken all at the same time, because there are no differences in the stresses that are applied to each set of bonds here. But because of the dislocation here that we have, the load here is bigger than the loads in the other in any other bonds. Some set of bonds are therefore broken because they have more stress there. That set is broken, and other set is formed, as you can see here. So the dislocation moves one step from here to there, and in the next step it moves to the next step, and so on and so forth. So in each step, a set of bonds are broken and another set of bonds are formed, and the dislocation moves one unit cell further, and it continues doing that in a stepwise manner. And that is why the load which is required, or the stress is required, with the existence or availability of the dislocation is much lower than the case if you had only a perfect crystal. So this is why we say dislocations are not a bad thing. Actually, they allow the plastic deformation to happen at much lower stresses, as we say. Clear, Shabab? Any question? Any reply, so that I know I'm online with you, please?
Clear, Doctor.
Clear. All right. So this is the mechanics and mechanism of plastic deformation. By today's explanation, we have a full view, a full picture of how does the plastic deformation in the material happens. Unlike when we dealt with it in chapter 6, we said there is plastic deformation. We just looked at the slip. Today, we have the detailed explanation of how the plastic deformation, both in terms of the mechanics and mechanism which are involved, which is the dislocation movement in the material. When we say here, to summarize, basically the movement of the dislocation to the right, which we are looking, the movement of the dislocation from this direction to that direction, This is what I'm saying here. The movement of the dislocation to the right in this sequence, which we had, requires the breaking and the formation of only one set. This is what we need to emphasize and we need to understand. Only one set of bones per step is broken and the other set is formed, basically. And that's why the energy required, the stress required, the force required for the slip to happen is much less than in a dislocation, in a material which has dislocation is much less than in a perfect crystal, as we say. Dislocations move in, we need to say that, in a close pack directions, in a close pack, which we know now what is close pack direction. Dislocations move in a close pack directions within close pack planes. So these close pack directions also make close pack planes. I'm not going to go more into this issue. We don't need to go much more into this issue, but we need to also just to know the combination of close pack planes and close pack directions, because you have how many close pack planes and how many close pack directions, we will form what we refer to as the slip system in the material. So this is what we have. This is the slip system. The combination of close pack direction and close pack planes, we refer to it as a slip system. The more the system in the material, the more it is ductile, the weaker the material would be. So this is to summarize, and this is the generally what I wanted to say. Now, after this, what we want to look at is that we already looked at. I mean, if you remember, we said, and that is in the middle of that will be the performance. We talked about the pillars of the material science and engineering. And if we want to do any research, material research, we basically will have to involve all those three things together. So if you want to research anything in materials, to investigate, for example, the effect or how would you change the structure is with a certain process to affect the properties of the material, you need to look at all these three items or pillars: the properties, the process, and the structure. So basically, the properties of the material you can investigate using the different tests. You can use a tensile test, the impact test, a hardness test, different tests that you can use to determine the properties of the material. Processing, well, you can do different processing to change the material. You can strain harden the material. Strain harden يعني شنو؟ يعني you can stretch the material to make it stronger, for example. There are mechanical processes, there are chemical processes such as the alloying. You can alloy the material. There are thermal processes that you can do. You can heat treat the material, which will be the focus in chapter 9. You can heat treat the material and change these are all processes. And the structure of the material, which is how the internal components of the material look like. So that's the structure of the material, which we need to actually visualize. We need to see what the structure of the material is. So in any research in materials, we'll have that cycle actually. You need to look at this and this and this all together. What changes you do in terms of process, what happens to the material in terms of properties, but we always need to look at what happens to the structure, cause that change in the properties. Otherwise, you wouldn't be able to understand nor explain what happens in the material. So this is what we are at. Now, if we do the processing, let's say alloying, we change we change the carbon content, or we thermally heat treat the material, we find out that we have a change in the properties of the material. But how does that happen? We need to visualize the structure of the material. We need to see what happens to the material before we do that process and after we do that process, which caused that change in the properties of the material. So in order to do that, we need microscopic examination. This is what I want to say. Observation of the, for example, the grain structure. This is one of the ways that we can visualize. This is one thing that we visualize in the microscopic examination. Now, in order to do the microscopic examination, we don't just bring any material and we heat it, treat it, and then we come and put it under the microscope, for example, as I am showing here and there, and do that. We just cannot just put it there. There is a philosophy actually behind looking at the microstructure, at the grains, for example, under a microscope. So there is a meticulous process that we need to actually do in order to be able to see the grain boundaries. مو هاللون كذي بس تجيب وتحطه تحت الميكروسكوب تقدر تشوف الجرينز. No, it's not like that. There is knowledge and philosophy we need to use. Actually, from what we learned last lecture, we are going to come back today and see how does this happen. So in the process of doing that, there is actually in the sample, you need to do what we refer to as sample preparation for microscopy. This is for the visualization of the microstructure under a microscope. So what do we need to do? We need to first of all prepare the sample. So there is preparation requires meticulous grinding and polishing of the surface. So the surface that you bring has to be grounded and has to be polished in different sequences. Let me stop that a little bit and go, yes, keep, and go and show that file, which I guess it's opened. No, yeah, it is open, and this is what I was saying. So we have pillars of material science and engineering: structure, properties, and process. As we said, I'm showing the pillars here just to make it fun. So if we need to investigate one, we need to go and see all the other ones. And in doing that, we need to do microscopic examination or visualization of the microstructure. We start with what we refer to as cutting. So first of all, the specimen that you will be having, for example, let's say it is a tensile test machine. After the tensile test, it is a tensile test specimen. After doing the tensile test, the specimen looks like the tensile test specimen. After breaking, basically, will look something like that. After let's say it is necked and it is formed a cup cone failure, basically. I mean something like this. So you need to sample that. Basically, you need to take a sample of the material and to see what the microstructure is. Now, in terms of seeing what the microstructure is, you can sample from here, but if you sample from here, the material would have the form. So this is after going through plastic deformation. Normally in our machine there, the loading is done on the shoulders here, and the shoulders which we have here. So shoulders, the grip looks like that, sorry for drawing this like that. So the load is applied there. So basically this part of the specimen does not go through any deformation, and that's why we normally cut from here and see what the original microstructure looks like. So basically, we do the heat treatment of the specimen before we do the tensile testing, and once we do the tensile testing, then we cut from here to get that part, because this does not go through any plastic deformation. Plastic deformation causes the material grains to change. For example, if I'm cutting from here and it looks like that, if I'm cutting from here, it would look elongated, basically the grain. So it will not be giving you the original shape of the material. So this is what we basically do. We cut it, and that is what we are referring to cutting. I'll go back to to the Word document here. So this is what we do. The first process of the visualization of the material or microstructure visualization will be cutting the specimen down into a smaller piece where you can control better. The second part, once you do the cutting and get a small piece of that, you do the mounting in something called the mounting press. So basically you mount the specimen. Don't I have a picture like this? I have pictures here, but I thought I had picture, but I found out that last time I had the pictures and I just erased them. No, not mounting pressure. Oh, this is basically a mounting press. What we have looks something like that. يعني it is the Bohler company. You can see guys my internet صح ولا لا? Hello?
يعني كده دكتور.
Yes, doctor.
Okay. So the machine looks like that basically. In the lab time we are going to go through that and see, but يعني this is a mounting press that we put the material inside there, it goes inside and then it presses the material and it comes out with the specimen mounted specimen. Can we do mounted picture of the Akka. Okay, good. Let's go to the images, maybe better. Inshallah, ما يطلع عندنا Akka. This picture is excellent. So we can look at that picture. When you mount this, this is a different mounting specimen than ours. The mounted specimen would look like that. This is the mount. We use backplate in our lab. We will take the lab on that. The videos we will see that. So this is basically the backplate that we put in, and that is our specimen that we have. This is the specimen. We normally mount the specimen like this in order, actually, any specimen that you will be cutting will have hard edges. So it will be difficult to do the grinding and polishing later on. With mounting it like that, it will make life easier if you are doing hand grinding and polishing. And in the machine, it requires to be mounted in this one because there are automatic machines as well. So this is what basically we refer to as mounting the specimen in the mounting by the mounting press and putting it and mounting it in the specimen of this is a polymer, of course, the backplate. Let's keep it, maybe we will need it. So basically we will go through and mount the specimen in the mounting press. Once we do that, we do the grinding. Basically it's a grinding process that you use some kind of grinding, rotating disc basically is used to do that. And the grinding is done with different grit sizes actually. We can also see that, I think it's worthwhile looking here. We say grinding. These are grinding papers that we could use basically, and like this. And the grinding papers have different grits in them. You see, the number of grits on them are different. You would be using the number of grits smaller, the paper would be much rougher. And the more the number of grits there, الحبيبات عليها, the more number of grits there, the smoother the material would be. So basically we start with the lower number of grits, go to the higher number of grits to cut the specimen first, to clean the specimen from everything at the beginning with the more coarser grits there. And then we go smoother and smoother, which we want to make the material more smooth. So this is how we start. We start with 120 grit size, and then we grind with in the second step with 240, then with 300, 400, then 600, until we go to 1200 grit size. But this is done by step, and this is basically for the steels. This will be work. Sometimes if we want to get rid of that step, it's fine. It will give normal and good results as well. So basically we do the grinding, and this of course it's a meticulous job. It takes a lot of time to do all that. I need to show that it takes a lot of time, because later you will understand why I am saying that. And then we do the polishing. In the polishing, we basically use same paper size. It's like circular like that, but it's not grinding papers. These are polishers, which are basically a kind of a cloth. We will see that in the lab. It's a kind of a cloth, and we use also diamond paste as abrasives there. And we use first of all the 3 microns diamond paste to do a certain polishing, and then we go for the final polishing, which we use 1 micron diamond paste. So basically we are going from very coarse grinding to very, very, very smooth up to 1 micron diamond, 1 micron level of surface. So what we are doing with this process, actually, we are getting the material to be very, very smooth. We will see in a minute why we are doing that. Once we finish that, then we do what we refer to as the etching. Etching is chemically attacking the surface that we have, that the specimen that we showed before. We attack the surface by an acid. Basically we call it methyl or nitric acid. Of course we dilute that. Normally we use 3%, 4%, and sometimes 5% diluted nitric acid, and we put the specimen in it. We attack the surface, that very smooth surface that we made. We attack it, and then that allows what the microstructure visualization. Once we attack it enough, then we go in the microscope and visualize the microstructure of the material, basically in this case the grains, and we will be able to see the grains. So how does that happen? I explained the process now, and what are the steps which we use to do that. I've shown a little bit more detail than here. So we have meticulous grinding and polishing is done. Then the microstructure is revealed by the attack using an etchant, chemical reagent. Preferential attack of grain boundaries will happen, and the grain boundaries we are able to see them. So what's the philosophy there that allows us to see? Why don't we just skip the grinding and polishing, all that meticulous job that we do, and the etching as well, and put the specimen under the microscope, and we are able to see the grains? No, that's not possible. How is it that we will see? If we don't do all these steps and look at the microstructure of the material like that, we will just see the surface finish. We will just see the surface of the material. How is it that we are enabled to see the grain boundaries there, the grains basically, which shows us the grains in the material? Let us go back what we have explained last time. First of all, let me remind you of what we have covered last lecture. We said in polycrystalline materials, where you have different crystals forming due to the different temperatures in the material, which cause the random orientations of the atoms in the material. The orientations here on this way, this is in this way, that is in this way, and they become bigger and bigger in different orientations, and they impinge each other when they meet, basically. And there is basically a mismatch between this grain and the other grain due to the different orientations that you have there. And this is where are we? And this is where the grain boundaries basically develop. At the grain boundaries, which is a mismatch, we said we have atoms, a lot of atoms, which are not having enough bonding. There are a lot of gaps, as you could see here, and voids. The grain boundary is actually a place which is a weakness, is an imperfection in the material, unlike the grain itself. Unlike the grain itself, within the grain, I mean, the bonds are all complete. There is no much, the atomic packing factor is the highest. You don't have vacancies here. Atoms are not having يعني missing bonds. Here you have atoms with missing bonds. They need to bond actually. Then we can say that the atoms are not stable at the grain boundaries. Therefore, so since the atoms are not stable at the grain boundaries, this means that they want to make bonding. صح? They want to make bonds, like what you have when corrosion happens. Like if you have a material, let's say the steel, for example, why does the corrosion happen? Because basically the outer surface atoms there, they lack some bondings there. The inner ones are all bonded together very well there. But the outer surface, there is some missing bonds there. So what do? They are unstable. In order to stabilize themselves, they react with the outer material, any material outside, and that's why the corrosion happens. Now here, you don't have things which are with high energy. At the grain boundary, you have the same condition as you have the outer surface here. So they are not stable. They want to bond. And this causes what we refer to as that at the grain boundaries here, the grains or the atoms are more chemically reactive. This is what we said last time. They are more chemically reactive. Chemically reactive meaning that if you put it in a reaction environment, they are going to react faster. Because why? Because they are the ones which are missing, having a missing bonds there. They are more, they can more react chemically and faster react in order to go to stable configuration. And this is what we use actually. This philosophy, this knowledge is what we use, what we refer to as the interfacial surface energy difference between the grain and the grain boundary, is what we use basically to visualize the microstructure of the material. First, in these processes that we do in the stage 1, the grinding and the polishing, what we do is that we try to get a very straight surface of the microstructure. At the beginning, it was having a lot of this and that. We try to cut that and grind that and then polish it in order to have only the difference between the ups and downs there of maximum, let's say, as we have seen there, of 1 micron. And that's why we use a 3 micron diamond paste, and then we end up with 1 micron. So maximum that you could be having there is 1 micron only, which is 1 times 10 to the minus 6. So we do that very smoothly in order to help us when we attack the specimen to be able to have that contrast actually. If we had all those now, so the next step will be attacking it with an agent. What does this agent do? The chemical, the acid that we add there, what it does is that when you attack the specimen with that, at, let's say, in here, the acid is going to react, but very slowly. But at the grain boundary, the acid is going to react much faster. Why? Because the atoms there are prepared to do the reaction. And that's why grooves actually, the reaction here, the atoms are going to fly in the reaction here. They are going to be removed in the reaction here more faster than the grains itself. Here the same thing. At the grain boundaries, the atoms are going to react with the acid much more faster. So what does that do? That creates actually a groove at the grain boundary. The atoms get eaten there at the grain boundary faster than within the grain. So what does that happen? What does that do? It makes what we refer to as a channels there. This channel, which you can see there, is made by the agent which we are adding. Why here the material is eaten faster? يتآكل أكثر لأن the atoms are much more energetic there. They are much more chemically reactive. So this forms actually channels at the grain boundaries there. نفس الجداول يعني. They form channels at the grain boundary. But within the, so because the layer there, as you can see, this is within the grain, and this is at the grain boundary. It causes the development of those channels, if you want to say. Why do we make the surface very straight? Well, if the surface is not very straight and it has all that, then if you put an acid there, well, it would not show really the contrast between the straight surface and the ones which is eaten by the acid there. There will not be any contrast there. ما بيكون في فرق بينهم. And that's why we make sure we have a very straight surface first. Then this will be successful. When you add the agent, it will make these grooves, which will show. If these were there with the grooves, you wouldn't be able to recognize the grain boundaries there. So once we do the etching and the grooves are formed, if you put the specimen under a microscope, of course this is a light microscope, the beam of light hits the surface here. When it hits within the grain here, the light reflects back. So what you will be seeing, you will see light. You will see light color, white color basically. But when the light hits the groove side, actually, because the groove is at an angle, these channels are grooves at an angle, the light is going to reflect back to somewhere else. And that's why these places you will see them as black lines there. And this is how you are able to see the grain boundaries in the material, and therefore visualize what the size of the grains that you are having there. So this actually, the effect that these features scatter the incident line and create optical contrast is what we use in order to see the grain boundaries in the material. So this is the philosophy behind looking at, and this is the knowledge that we use in order to visualize the microscope or to see the microscopic the grain boundaries of the material using the microscopic examination. Any questions, guys?
دكتور
Yes.
وش إذا شفنا جرين باودر وش نستنتج يعني من الاختبار نفسه؟
من الاختبار يعني of course we don't only visualize the grain boundaries, we visualize the size of the grain, we can visualize second phase boundaries, and of course I need to say this also, this is just, I'm going very superficially in the microscopic examination. يعني أنا قاعد بس ألمس لكم because this is a very deep area. There are books on the microscopic examination, and we have different types of examinations as well that we could do. For different phases, we use different philosophies, we use different agents. Even the agents will be different. Here we are using Nital. For different visualizations or looking at different things, we use, for example, if you have multi-phase states, how will you see the different phases of the material? So this is a very, very deep area. But specifically for here, because I don't want to go much into details of that, just give the students a glance or a good information on how this is done. A grain boundary is very important. In the same way, in the other microscopic examinations, you would see how many phases you have in the material and how much of each phases you have in the material. That affects the properties of the material, صح? In our case, when you're looking at the grain boundaries, you're looking at the grain sizes. The grain size has an effect on the property of the material. You know, when you did that process, the material became stronger. Why? When you look at the structure, you see, for example, that you have a very fine grain structure. So you know the reason was that this process caused the grain structure refinement, which caused the properties of the material. So this is how it goes. You need to look at the structure when you do any process. When you test the material and you see that change, you look at the structure and you find out the reason for why that change happened in the material. Clear?
Yes, Doctor.
Okay. So, and also we just need to shed light at that we don't have only microscopes there, but there are also other other means of or tools to see the microstructure of the material. We have the optical microscopy, of course, the same as what we have mentioned here. Uh, an optical microscopy, which uses light basically, optical refers to the light, is actually limited to 2000 times the magnification. So how much magnification you can make? Up to 2000 times, يعني 2000 مرة تكبير. So 2000 times magnification. But we have also others which are referred to as the electron microscopes. And the electron microscopes are much more capable than the light because they use electron waves actually instead of light, and we know that the electron waves have much smaller wavelength, much smaller, up to 0.003 nanometers there, and they can reveal microstructures up to 1 million times the magnification. You can compare 2000 times to 1 million, so this is a big jump into the magnification that we have. The electron microscope have two types. This is the first type, which we refer to as a scanning electron microscope. Normally it is referred to as the SEM, the short form of it, scanning electron microscope. In the scanning electron microscopes, very similar optical preparation, like what we said, mounting, grinding, all that, and polishing is used normally in order to see the microstructure of the material. So the sample preparation is the same, but also the scanning electron microscope also allows us to see the microstructure of the material without any preparation actually. So you can do what we refer to as the fractography, and you could to see the material fracture, for example. If you are looking at the fracture, of course you don't need to polish, you want to see how the fracture happens. So the scanning electron microscope allow us to see the fracture materials and the details of that. It could go to a magnification of 50 times, يعني 50,000 magnification. It's not 5,000, it's 50 times. So there is a big difference between the two here, 2,000 to 50,000. This is the scanning electron microscope. And we have also the transmission electron microscope, which is abbreviated by TEM here, the transmission electron microscope. In the transmission electron microscope, the samples are prepared, of course, differently. They are very, very small. Actually, if you are testing, for example, or you want to examine a steel or any material, you need to make a very, very thin material, which we refer to as electron transparent samples. And how is that? Is that you make the sample very, very thin, that when you eject the electron beams there, it would be able to pass the material, and behind that will be the illuminating surface that is there. The electrons pass and they make a picture. Where they pass less, they make less electron injected here. When where they pass more, they will make more injections and illumination of the surface that you have here. So that's the basic idea to see this. So you need a very thin specimen. Basically, these locations are looked at through the TIM, and because it can go to magnifications of about 1 million times magnification. This is basically an electron microscope that you can see. Sorry, this is an optical microscope that you can see in our labs. Also, we have many of them. This is a scanning electron microscope. It's a much bigger device. As you can see, this is much simpler device you can use, but this you can see the micron level using up to 2000 times magnification. And normally my work involves only microscopes there. Scanning electron microscopes are much bigger devices there. As you can see, you need an electron chamber, electron beam chamber there. The SEM is designed also for direct studying of surfaces of solid objects. So you can see the fractography, as we say, which is the failing of material. but this is much costly, of course. You need to understand that. The scanning electron microscope that uses electrons or rather than light to form the image, and there are many advantages of the scanning electron microscope over the light microscopes. If we can just look at this to compare between the light microscope there and the SEM microscope using the same image which we have here. The SEM has large depth of field, basically. So see, depth of field and a greater resolution and larger, higher magnification compared to the light. We have 2000 compared to 50,000, causes the image to be that clear. You see, this is using a light microscope, and this is using a SEM microscope, a scanning electron microscope, as if you are looking at a three-dimensional image, basically. So what makes the material looks, the image look like that? It's the three reasons which we are saying here: higher magnification, larger depth of field, and a greater resolution makes the SEM one of the most heavily used instrument in the research and in the industries, especially in the semiconductors, for example. Actually, why does this is allowed? Actually, is allowed because this large depth of field allows large amount of sample to be in focus at the same time. Large magnification and large amount of samples in the material which can be collected and viewed actually at the same time. That causes the material to look like that. This is the last one, which is the TEM. This is the transition or transmission, if you want, electron microscopes. Of course, you don't need to know the pictures, they're just having an idea. And this is what it can do, basically. You can see here high resolution using the TEM of a tilt grain boundary. You remember the tilt grain boundary here? That's it. It's not an easily looked at boundary. Actually, this is a boundary, basically. You can see from here and from there. This is very difficult to see in an optical microscope, basically, and even maybe in the SEM as well. You can easily see it in the TEM here. This figure is showing us 8 grains in different orientations, as you could see there. The orientations are different and the reflections are different. You have weak diffraction there. This is the grain boundary. This is actually for ultra fine grains. These are very, very fine grains. You can see the measure here is I mean, this measure from here to there is 8 nanometer. Yani from here to there, it is 8 nanometers there. So what is the thickness from here to there that we are looking at? That thickness is very, very small, which can be seen by a TEM microscope there. This comes to the end of this chapter, so I have finished. I will say keep. Any questions, guys? Any questions, guys? Hello?
دكتور لاب اليوم بيكون عنده الوبتيك الاختبار يعني.
Today's lab, no. Today's lab will be about the other test, which is the impact test and the hardness test. We will see that together. This is what we will do.
Okay.
Okay. Any questions, guys?
Clear, doctor.
And no questions? Let me stop the. Oh no, this is the internet. Let me stop the recording. Okay, so that doesn't take longer.